Aloha, welcome to Pharmacology. We'll move the PowerPoint slides and get started today. There they are. Today we're going to talk more about basic principles in pharmacology. Again, 1.3, 1.4, and 1.5 are very long versions of basic principles in pharmacology, and these are very, very important, as abstract and meaningless as they might seem at first. If you can grab the information and put it in your brain somewhere for the rest of your life, this information will be very important in understanding toxic interactions of medications. A lot of people believe the way to understand the toxic interactions is to memorize all these different things about medications, and I don't think that's the case at all. I think if you have a really good handle on how the body deals with medications, then I think you'll have a much better handle than just trying to memorize things. Well, that being said, let's move to the lecture. All right, a lot of pharmacology curriculums will say this: oh, most drugs are weak acids and weak bases, and then move on with absolutely no explanation as to why that is. And a lot of people don't even understand what this means. And so the first time I did this lecture back in 2008, my description of this was horrible. And so we've overcompensated and made lots of slides to explain why drugs are weak acids and weak bases, at least the near entirety of them. And here's the punchline right here: most drugs are weak acids or weak bases because only small changes in pH are required to shift between a fat-soluble and a water-soluble form. So if you're in the dental hygiene business, this is a very important concept. They'll teach you that lidocaine, as a numbing anesthetic, any of the local anesthetics that are based on lidocaine, will be more effective in normal tissue than they are in inflamed tissue, because inflamed tissue is more acidic, and the more acidic the environment, the less likely the lidocaine is able to easily pass through cell membranes. And this is another reason why certain medications can't be mixed together without forming a deadly set of particulates inside of the IV tubing. And so this is the point right here. This is a very important concept in mixing medications. This is a very important concept of why medications work in certain pHs, but not others. And so that's why we go through this. All right, from our first chemistry lecture, we remember that any substance that releases the hydrogen ion, which is the same thing as a proton, into the water, we're going to call that an acid. Well, anything that can bind to that hydrogen and pull it from the water will be considered a base. It is a base. And I promised someday I'd put bicarbonate instead of hydroxide. Oh, and we missed the bicarbonate slide. How did that not get in here? That's why. And so we're going to stall. Open. U. Again, any substance that can release a hydrogen ion, a proton, into the water is an acid. Any substance that can bind a hydrogen ion from the water is a base. And so again, this is the game of acids and bases. By sending a proton one direction, we conceptually are moving electrons the other direction. All right, well, hydroxide ions are fun in chemistry class. In humans, our base, our buffering system, is bicarbonate. And we've wanted to include bicarbonate in the show for quite a while. So any substance that can bind a hydrogen ion in the water and remove it from the water is a base. And so we're going to look at bicarbonate levels as we study acid-base balances. And the bicarbonate level will tell us something about the acidity of the body. And so that's why we added that slide. All right, so here's a quiz question. What is pH? Oh, it's a measure of acidity, and everyone checks that. But pH is also a measure of alkalinity, how basic something is. All right, it gets more complicated than that, but anything with a pH of greater than 7 means there is an excess of base in the water. pH less than 7 means there's an excess of protons. And so make sure you understand that concept. pH less than 7 means there's an excess of protons in the solution. An alkaline solution has an excess of base compared to the acids, the protons. And so keep this in mind. Water, neutral pH is 7. Physiologic pH in a human, somewhere around 7.35, 7.36, 7.4, depending on what you read, slightly on the alkaline side. And so if somebody's pH is 7.1, that's a disaster. People can't really tolerate pHs much less than 7.2. If you have somebody who's been a DKA and diabetic ketoacidosis for a long time, they might be able to tolerate lower pHs because they've been changing chronically. But physiologic pH is this right here, and your body requires this pH for all of the chemistry to function properly for reasons that we're getting ready to explain, hopefully. All right, so most drugs are weak acids and weak bases, so I guess the first thing we should talk about is why drugs aren't strong acids and strong bases, and really this has to do with delivering the drug either from the blood supply or even from the stomach, and then getting the drug where it needs to go. All right, so we're going to start with a beaker of water. That's what this is. It's a beaker for those of you yet to take chemistry. And then here's my cartoon of a beaker of water. Remember, water is H2O, and it is a polar solvent. And so things that form ions will dissolve into the polar solvent. And so there's sodium chloride. You guys know what salt is. If you put sodium chloride into the water, you have sodium ions and chloride ions. These are very important things to talk about when we start talking about excitable membranes like cardiac conduction, neurotransmission. And you guys know what salt is. You can taste it in the ocean. You see it in the grocery store. Right? So it's not a hard concept. So once we start talking about sodium channel blockers and chloride channel blockers, just remember we're just talking about regulation of salt in the body. All right, so sodium chloride is a white powder. I think I put that somewhere, and we're going to put it in the solution. And what does it do? Well, it disappears. All right, well, we know it's there. We just can't see it, all right, because what has it done? It's dissolved, all right? And so the sodium chloride, it didn't dissolve. What happened is it left its solid form and went into its ionic form. And so the solid completely dissociated into its ionic form. And now we have sodium ions and chloride ions in the solution. We can't see them in their ionic form. But notice this arrow right here. Notice the equation has gone completely to the right. The sodium chloride in its powder form, in its solid form, has completely dissociated into its ions. And that's what strong means, complete dissociation. All right, but we're not going to talk about sodium chloride as a strong acid or a strong base, but let's actually talk about strong acids and strong bases. I just wanted you to give the example of salt because that makes sense to you. You put salt in the water, it dissolves, it disappears. And it completely disappears because the equation moves to the right. All right, let's take a strong acid like hydrogen chloride, which is a white powder at certain temperatures and pressures. I do actually get emails about that. All right, so we're going to imagine that hydrogen chloride at this temperature and this pressure is a whitish powder that I'm going to put into the water, and barring the huge exothalamic reaction, you can just ignore all that. Hydrogen chloride is a powder that we can put in the water. And what it'll do, it'll completely dissolve. It'll disappear, but it doesn't disappear. It dissolves into its ions. It dissociates into its ions. And again, when I put the hydrogen chloride into the water, what did it do? It liberated a hydrogen ion. That's what defines it as an acid, because it liberated a hydrogen ion into the water. And then to balance that, we have chloride ions as well. So now we have an acidic solution, and it's called a strong acid for this reason right here. The equation moves completely to the right. The white powder, the solid, has completely dissociated into its ionic form. So strong just means complete dissociation. It doesn't matter how much it burns. Hydrogen chloride is a strong acid, a very strong acid. And you have hydrogen chloride in your stomach to sterilize the food that you eat. And its pH is 2, less than 2, depending on the things you read. Let's talk about a strong base. All right, well, we'll start with water again. We're going to take some sodium hydroxide powder and put it into the water, hopefully without too many emails. And once we put the sodium hydroxide into the water, what does it do? It completely dissociates into sodium ions and then hydroxide ions. And because the hydroxides can take the proton out of the water and turn it into water, we call it a base. Right? But why this is a strong base is this arrow right here. The white powder, the solid form, has completely dissociated into its ionic form, and that's what makes this a strong base. So strong just means complete dissociation. All right, well, that complete dissociation, that's not very useful for us in drug delivery. We don't want drugs to completely dissociate. We want them to be able to balance between a fat-soluble form and a water-soluble form. That really helps us deliver the medication. So that's an important part of not only absorption but delivery and elimination as well. And so most drugs are weak acids or weak bases, quite simply because we only want a small pH change to shift them from a fat-soluble to a water-soluble form. That's why. So let's go with that. Let's talk about that. Weak means incomplete dissociation in water. So let's talk about a weak acid. Here we're going to talk about aspirin. Aspirin is a white powder, and we're going to take any white powder. R is a variable group. Here we have a carboxylic acid that's going to liberate a proton. We're going to imagine that this is where the proton is liberated from an acid, and that'll be fine. So we're going to take this aspirin, or we're going to take any kind of weak acid and put it in the water. And what happens? Well, if you take an aspirin and throw it in the water, it's not going to completely dissolve. It'll partially dissolve, but it won't completely dissolve. And so this is what shows us this is a weak acid. We put this into the water, it liberates that proton right there, and so now I have proton ions, and then I have the negative ionic form of the aspirin right here. And notice that the equation's running both ways. I have some solid that doesn't dissolve, and then I have some ionic form. And most drugs are weak acids and weak bases for this reason right here. All right, so now what do I have in the solution? I have the uncharged form of the aspirin because there's no ionic charge on it. It's not positively charged or negatively charged. And then on the right, I have the ionic form of the aspirin, which is negatively charged. Now I'm going to ask you right now, here's a quiz question online. Which one of these do you think will be more fat soluble? Which one of these do you think is more water soluble? And that being said, we'll tell you the answer. The uncharged form of the drug is going to be more fat soluble, and the ionic form of the drug is going to be more water soluble. And so having this balance between a fat soluble and a water soluble form of the drug is a strategy that we use in developing medications because this is essential for not only absorption but delivery and elimination. All right, so in the books they talk about mass action. That sounds like a really cool word. You guys might know it as saturated. It means almost the same thing. So let's go back and talk about table salt because you guys understand this concept. All right, we took the white powder, the sodium chloride, we put it in the water, it completely disappeared, but we know that what really happened is it dissolved into its ionic form, positively charged sodium ions and negatively charged chloride ions. Great. Well, what happens if we just keep adding salt and adding salt and adding salt and adding salt and adding salt? All right, well, the solution becomes saturated with salt, and eventually we can't dissolve any more salt into the solution because the solution's already too salty as it is, so it won't allow any more salt to be dissolved. And so, as with anything that dissolves into the water, there comes a point where you added enough and it just won't dissolve anymore. Why? Because all of those sodium chloride ions that have saturated the water, well, they start pushing the equation in the opposite direction. They start pushing the equation to the left. Now, when we started, we took the sodium chloride, we put it in the water, it completely dissolved, moving the equation to the right. But eventually, we put so much salt in the water that those ions push back, and they start causing mass action against the dissolution of this right here. So that's what mass action means. It just means saturated. And you can try this. You can stir up the water with the salt, and eventually you just can't dissolve any more salt. All right, so there's my beaker of water again. We're going to make hydrochloric acid, which is a very strong acid. And remember, when we have hydrochloric acid, we have a solution that's full of these hydrogen ions. All right, and there's nothing really to absorb them out of the water. And so we have this hydrogen ion in solution. So this solution is very acidic. Its pH is less than 7. All right, let's take the aspirin and throw it in this acidic solution, kind of like taking an aspirin and then putting it in your stomach. All right, so now we've put the aspirin into solution. All right, now this proton, remember this is the proton that we wanted to come off of the aspirin. This is the proton we want to come off of this weak acid. And this solution is already full of protons, all right, already full of acidity. This acidic solution, what kind of mass action do you think it's going to put on this proton trying to come off? This is going to try to come off and be one of these guys over here. The problem is we have a bunch of these guys right here pushing the equation in the opposite direction, as if this solution is already saturated with hydrogen ions. So that proton that wants to come off the aspirin, it can't because of mass action. The protons in the water, the acidic solution, those hydrogen ions in the solution are pushing back on the equation, and so they're keeping the aspirin in its fat-soluble form. So when you take an aspirin and it sits in your stomach, like a lot of medication, they sit in your stomach, they can sit in the lipid-soluble form, and being the lipid-soluble form, they're more easily passed through membranes. So in acidic solutions, the aspirin is going to be more fat-soluble. Let's start with our beaker of water. Make a strong base, sodium hydroxide. Sodium hydroxide is a very strong base because it's completely dissociated its ions into solution. And so now I have a solution that's very basic because it has this excess of hydroxide ions. And remember, these hydroxide ions are ready to pull a proton out of the water and neutralize it, because when the hydroxide pulls the proton out of the water, then it just turns into water. All right, so there's my aspirin, there's my weak acid, and okay, again, when I put this into solution, we want this proton to come off the aspirin. All right, and here's this hydroxide ion more than willing to take that proton off of the aspirin. So what happens? Mass action is pushing the equation to the right because of the basic solution. So because the solution is basic, it's pulling the proton off the aspirin. So in basic solutions, the aspirin is in its water-soluble form. And so in basic solutions, the aspirin's more water-soluble, and that makes sense to get when it's in the stomach, it can be fat-soluble to pass through membranes, and then when it gets out of the stomach, there's a significant pH change, and that change in pH can make the drug more water-soluble. And so this is a basic strategy of getting across membranes, is like we'll change it when it changes. When the environment, the pH of the environment changes just a little bit, the drug can shift back and forth between either a water-soluble or a fat-soluble form. All right, well, there is this perfect balance. There's a pH where there's a balance between the fat-soluble and the water-soluble forms of the drug, and we call that the pKa. And so drugs will have a pK. If you're in the advanced pharmacology business, this will be something you want to spend a little more time studying. For the rest of us, we don't use pKa too much in the clinical setting, although understanding this concept is essential in understanding why certain medications cannot be mixed together. They cannot be mixed in the same syringe. They cannot be mixed in the same IV tubing. And if you're in a critical situation, taking care of critical patients, you'll find yourself calling the pharmacist or finding out from the pharmacist what drugs can be mixed together through the IV tubing. And it's because of a concept called the pKa. And the pKa describes a drug quite simply as the balance between its charged form and its uncharged form. It's just quite simply a description of the drug. It tells us basically how basic or acidic a solution needs to be for there to be balance between the two forms. And then that tells us the property of the medication. Those of you in advanced chemistry classes, you know there's this thing out there called a pKb. We don't use a pKb in pharmacology because we're only interested in a protonated form of the drug or the non-protonated form of the drug, and that doesn't matter if the protonated or unprotonated form is an acid or a base. And so we don't use pKbs, and pKa is just the inversion of that anyway. So we use pKa's in pharmacology, in clinical pharmacology. And again, for this reason right here, most drugs are weak acids and weak bases because only small changes in pH are required to shift them between a lipid-soluble form and a water-soluble form. And this is very important. So you want your drug, if it's in solution, if it's mixed in IV like normal saline, you want that drug to be water-soluble as it goes into the veins. Because if you have little globs of fat or little pieces of aspirin, little solids, if you have solids and particulates, particles of solids in your IV solutions, that can result in lethal consequences. That can result in blood clots and death. And so having particulates in the IV, if you have a clear IV fluid and it starts to turn colors, turn white, like there's some solution, there's something in the solution that's turning into a solid, maybe there's been a pH change and whatever's in the IV solution is no longer water soluble. And so knowing that certain things cannot be mixed because of their pKa's, because of this thing right here, is essential in understanding toxic interactions between medications. All of that comes from Michaelis-Menten, which is where Henderson-Hasselbalch comes from. For those of you keeping score, this is the logarithm of that fraction. These brackets stand for concentration. The R is a variable group, and so H is the protonated form of the drug, where R is the unprotonated form of the drug. And when we use this, then we don't have pKb's involved. And so the protonated form on top of the fraction, the unprotonated form on the bottom of the fraction, take the logarithm of that, and you have the pKa minus the pH. All right. Transformation is the chemical changing of the drug by the body. All right, dynamics is what the drug does, and kinetics is what the body does to the drug. And so transformation is a part of kinetics. In pharmacology, when we talk about transformation, we're usually talking about liver transformation. Your liver is the big transformer. Your liver has trust issues. Everything you eat has to go to the liver first for inspection, and the liver is always trying to change all the little chemicals that it sees. But actually, transformation occurs everywhere. It can occur outside of the liver, anywhere. That's what peripheral transformation means, anywhere else. And then there's GI transformation as well. We have transformation enzymes in our gastrointestinal tract, that is, we absorb the food even to go to the liver through the portal blood supply. There's transformation going on inside of the gastrointestinal tract as well. And so transformation occurs everywhere, but liver transformation is what we like to talk about. Elimination is the removal of drug from the body. And so this is an important concept when we talk about pharmacology. When we talk about medications, there needs to be a way for those medications to get out, and that's called elimination. And these are the major forms of elimination right here. Look, when you do anesthesia and you give somebody a gaseous anesthetic, they eliminate the drug through their lungs. Okay. With that being said, this is what happens the rest of the time. Renal and hepatic elimination. All right, renal elimination means something's eliminated by the kidneys, and then hepatic elimination, there's two ways to go about that. We can either pass things through our stool, or into the bile, which eventually ends up in our stool. And most drugs usually require both renal elimination and hepatic transformation and elimination as well. All right, let's take a step here. Let's take a moment to talk about first and zero order kinetics. I got a lot of emails asking me to explain this until we put this up. And so you'll hear about this. It's a rather advanced concept, but actually it's very, very, very simple to understand. And so I think we talk about, good. As far as memorizing stuff goes, here's your memorization right here. If eliminating a drug has to do with a concentration, that means higher concentration means higher rate of elimination. Lower concentration results in lower elimination. All right, so if you have high concentration of drug in the patient and they're eliminating the drug more quickly than they would at lower concentration, well, that's just considered a first-order process, a first-order elimination. Some drugs are just eliminated at a constant rate. It doesn't matter what the concentration is. They're just eliminated at this fixed rate. That's called zero-order elimination. And let's explain a little bit, hopefully, why that is. All right, to explain the cartoon to you, here is drug inside of the body, and here is drug outside of the body. It's been eliminated into the urine. That's what we want you to imagine right there. All right. Here's my drug elimination system. There's all sorts of ways to eliminate drugs. Here I have nice little pumps that pump the drug out. It's not always the case, but these are my drug elimination system. And here I have 4. Your body has many, many, many more, but they can be saturated as well. And so to make things simple, here are my drug elimination pumps for this drug, and we'll just divide them up into 4. All right, so, well, this is a first order process right here. My concentration is 1, my rate of elimination is 1. My concentration is 2, my rate of elimination is 2. My concentration is 3, my rate of elimination is 3. My concentration is 4, my rate of elimination is 4. All right, so we'll talk a little bit about graphs. Graphs have a label. They have axes that are labeled. And then here this shows us the property of what we were looking at. How does an independent variable result in a dependent variable? And so if the concentration is 1, my rate of elimination is 2. If my concentration was 4, my rate of elimination is 4. And see that nice straight line? This all comes from linear equations. We're getting there. So this is first order kinetics. By the way, first order processes have anything to do where the concentration of something results in a higher rate of absorption, permeation, elimination. All of those are first order kinetics. All right. So here the drug concentration is higher drug concentration results in higher rate of elimination. It's called first order elimination. All right, so now let's go to zero order processes of this drug. All right, my concentration is 4, my rate of elimination is 4. We remember that. Here my drug concentration is 5, but notice we've saturated the elimination system, at least in this cartoon. And so when my drug concentration is 5, my rate of elimination remains constant at 4. Even if my drug concentration is 6, I've saturated the system, my rate of elimination remains at 4. Even if I add more and more and more drug, the receptors are saturated. We talked about this before when we talked about agonist dose response curves, and now we're talking about it again with elimination, that we've reached a point of maximum elimination and more drug is not going to result in more elimination. And so what we have here is a zero order process. Regardless of the concentration, our rate of elimination remains at 4. And we can graph that out just like this. Y is equal to 4, that's what they teach. And so if x is 4, y is 4. If x is 5, y is 4. If x is 7, y is 4. And so if the concentration is 4, the rate of elimination is 4. If the concentration of drug is 7, the rate of elimination is 4. It doesn't matter what the concentration of drug is. At this point, the rate of elimination remains at 4. And that's a zero order process, zero order kinetics. And it occurs to anything. If something is constant, has nothing to do with concentration, whether it's elimination, absorption, permeation, it's a zero order process. All right. And that all comes from linear equations. And linear equations can be drawn out in different ways. Here I have y is equal to some coefficient of x plus a constant, b being the coefficient, c being the constant. Sometimes they'll use m as a coefficient. Sometimes they'll use a function of y. But here, my dependent variable is equal to some coefficient of the independent variable plus concentration. Sounds ridiculously complicated, and it can be. Linear equations are lots of fun. I spend a lot of time making videos about linear equations. If you look carefully, you can find them. If you can't find them, let me know. I'll send them to you. But linear equations are called linear equations because they draw straight lines. And so here, my first order kinetics, this is a y is equal to x linear equation. And the way we make y equal to x, we'll just make our coefficient 1, make our constant 0, and now we have y is equal to x. And that's what we have here. All right, well, keep in mind that y is equal to x to the first power. And so whatever x is x to the first power. And this sounds silly with linear equations, but when we start getting into calculus, when you start getting into calculus, then those power signs over your variables become important because we're going to make them go up or make them go down depending on what we're doing. And so here is not only is y equal to x, but y is equal to x to the first power. And so x is equal to x to the first power. And that 1 over the x, that one exponent, that's where first order kinetics comes from. So you might even hear about second order kinetics where something is equal to x squared. We don't really even talk about second order kinetics in pharmacology because predominantly first order and zero order kinetics are primarily what we talk about. And so if you ever hear about second order kinetics, that's because they're dealing with something where the equation is in x2. It's no longer a linear equation. And so in the pharmacology business, we stay out of second order kinetics. We stick with first order kinetics and zero order kinetics. All right, let's talk about the zero order kinetics. All right, and that comes from linear equations. How do we make a y equal to 4? Because that's what we see here. All right, well, to do that, we'll make the coefficient of x 0. Oops, here, we'll go backwards. All right. Zero order kinetics comes from linear equations, and here we've drawn the linear equation out for you. Y is equal to 4, and remember linear equations comes from y is equal to some coefficient of x plus a constant. All right, so I showed you x to the first power. Something you want to remember about that constant over there is there's this imaginary x to the 0 power. And anything to the 0 power is equal to 1. And so I want you to keep that in mind when you're doing linear equations, preparing for a life full of calculus, that linear equation that they give you x, that's really x to the first power. And that constant they give you, that's really times x to the 0 power. And that'll be more helpful when you're thinking about plugging in these equations. All right, so we have that x to the 0 power. Remember, anything to the 0 power is equal to 1 because x to the first power is like one of those x's. So if there's no x's, there's still 1 times whatever's coming to the right. So please know this about exponents, that anything to the 0 power is quite simply equal to 1. It doesn't matter what is to the 0 power. Anything to the 0 power is quite simply equal to 1. All right, so this is what I wanted you to see. When you see linear equations, they'll draw y is equal to mx or bx or some coefficient of x plus a constant, but in your imagination I want you to see x to the first power and that constant being times x to the 0 power. Now we can turn our y equals 4, y is equal to 4 by going through this linear equation. All right, so y is equal to b times x to the first power. If I make b equal to 0, that completely eliminates x to the first power. And so now I have y is equal to c times x to the 0 power. And remember, x to the 0 power is just quite simply 1. And so if x is equal to 4, well, here, we'll add that. We'll make our constant 4. There we go. So now y is equal to 4, and remember, that's x to the 0 power. And so 4 to the 0 power is still 1. 5 to the 0 power is still 1. 6 to the 0 power is still 1. 7 to the 0 power is still 1. And so now I have x equals 4. And that little 0, that x to the 0 power, That's where zero order processes come from, because something to the 0 power is equal to 1, and it's the constant that's times the x to the 0 power. So when something's constant, we can consider it a 0 order process. And so that's what those things mean. And you'll hear about that in pharmacology if you read careful things or talk about people who understand drug elimination and kinetics. They'll talk about first order processes and 0 order processes. And anything that's first order, that just depends on whatever's going on, depends on the concentration. Anything that's 0 order doesn't depend on the concentration, it just occurs at a constant rate. And so that's my introduction to first and 0 order kinetics. Maybe someday we'll expand all of that. All right, so let's talk about a first order process called a half-life. Because a half-life is the amount of time required to lower the concentration of drug by half. And so notice that concentration is involved in the equation. So I know this half-lives are not a 0 order process, they're a first order process. All right, when they were teaching me half-lives, my physics teacher, Greg Benish, God bless his soul, taught it like this, that a guy a guy replaced his air conditioner with a heat pump, and he cut his electric bill in half. So he thought, well, he'll just go get another heat pump, and then his electric bill will be free. So please don't think that something's eliminated after the second half-life. That is not the case at all. Things are eliminated after about the 5th half-life. All right, so don't think 2 half-lives make a whole life, because that's not the case at all. Because what it is a half of a half of a half of a half. So again, the half-life is the amount of time required to lower the concentration of drug by half. All right, so here at time 0, the clock starts at 0, and so we're at the 0 half-life, meaning where we start. Things start at 0. Don't be confused by the 0 half-life. All right, and so that's the amount of drug in body. And after an hour, or after 1 half-life, the amount of drug in the body is half. All right, so 1 half-life has passed. If the half-life of a drug is 1 hour, then this is 1 hour. If the half-life of a drug is 12 hours, then 12 hours later, half of the drug in the body has been eliminated. So if the half-life of a drug is 1 hour, then after 1 hour, half of the drug has been eliminated. If the half-life of a drug is 4 hours, then after 4 hours, half the drug has been eliminated after its first half-life. After 2 half-lives, what's left? Half of half. Remember, the half-life is the amount of time to eliminate the concentration by half. And so now I'm in my second half-life, and by the second half-life, how much drug remains? 1/4. That means 3/4 have been eliminated, and I have lots of fun quiz questions about whether how much drug remains, how much drug has been eliminated. And so try to have a good handle on half-life, because people talk about that all the time. All right, so if the half-life of a drug is 1 hour, after 2 hours, 3/4 of the drug has been eliminated, meaning 1/4 of the drug remains. All right, well, at the third half-life, we're talking about half of a half of a half, which is 1/8. All right, so after the third half-life, 1/8 of the drug remains, which means 7/8 of the drug has been eliminated. So if the half-life of a drug is 1 hour, then after 3 hours, 7/8 of the drug has been eliminated. If the half-life is 4 hours, then after 12 hours, 7/8 of the drug has been eliminated. After 4 half-lives, what remains is 1/16, a half of a half of a half of a half. Yeah, and so 1/16 remains, meaning 15/16 has been eliminated. Well, after 5 or 6 half-lives, we give up, and we just consider the drug to be completely eliminated. 5, 6, depending on who you're arguing with. All right, so after 5 or 6 half-lives, we consider the drug to be completely eliminated. But what I wanted to show you is that the rate of elimination quite simply depends on concentration. So by definition, half-life. A drug with a half-life is a first-order process, elimination process. So what I want you to see here is that a lot of people think that after 2 half-lives, the drug has been completely eliminated. And we'll see board questions for various healthcare tracks asking about that. And remember, the drug is completely eliminated after 5 or 6 half-lives. All right, we'll go through some terminology. So drug accumulation occurs if the dosing interval is shorter than the fourth half-life. So that's why we want to know about half-lives. And so we're going to give a dose of a drug, and we want to have this target concentration. We want the target concentration of drug to be a certain amount, and we want it to kind of stay there within that range. And so to get the doses to accumulate, well, gee, if we wait 6 half-lives, we give the drug, and then we wait 6 half-lives, we give the drug again. Well, the drug's been completely eliminated. We haven't reached target concentration. So to get drug up to a target concentration, that concentration where we want the drug, then we have to dose it shorter than its 6th half-life. Here it says we need to dose it shorter than its 4th half-life for accumulation to occur. And that makes sense. All right, let's talk about volume of distribution. This is a really abstract concept that a lot of people have difficulty with, even when they are renowned experts. And so let's talk about the volume of distribution. All right, the volume of distribution, first off, is not a volume. All right, and so it's not a real volume. It's this abstract volume. It's an imaginary volume. The volume of distribution is an imaginary, an abstract volume. It's not a real volume. And so as long as we get that out of our minds quickly, then we can move through this. All right, so the volume of distribution tells us what? How extensively drug is distributed to the rest of the body compared to the plasma. And so drugs with a very small volume of distribution, you put them in the plasma, the drug stays in the plasma. That's a small distribution. All right, you put the drug in the plasma, it gets absorbed everywhere else and completely eliminated from the plasma. That's a very large volume of distribution. And so the smallest volume of distribution you can have is you put it in the plasma, it stays in the plasma. The largest volume of distribution you can have is you put it in the plasma and it completely disappears from the plasma because it's been absorbed by the rest of the body. All right, so let's make it more complicated than that. Here is any volume of water. It's measured in liters. And let's add any dose of drug measured in mass units. And eventually that drug will give us a concentration. And now we know how much drug is in solution compared to the volume of the drug. I'm sorry, the volume of the solution. We have a concentration. Simple enough. We know exactly how much was added to that compartment, and we know how big the compartment is. And so we have a concentration. And so we'll call it a compartment, and here we'll call it the total body water compartment. And so let's imagine we've taken this drug and put it into solution into a single compartment, and now we have a drug concentration, which is quite simply the dose of the drug over the whole body volume of water. Well, it'd be nice if it was that simple. Well, let's make it a little more complicated. Let's take the two body water compartments. Let's take the body water compartment and divide it into two compartments. One of them will be the plasma. One of them will be the rest of the body. And between the two of them, that's the total body. Don't be fooled, they're not the same size. One of them is much larger than the other. Our total body water is 0.6 liters per kilogram. That means 6/10 of our weight is water. 4/10 of our weight is stuff. But plasma is only 4/100 of our weight. And so the plasma only makes 4/100 of a liter for each kilogram. So notice our total body water is very large. Our plasma compartment is very small. So in a normal 70 kilogram person, plasma makes up about 3 liters. The total body makes up the 42 liters. All right, so we put a drug into the plasma and it's distributed evenly between the plasma and the rest of the body water compartments. Wow, that would be great. And if it was that simple, we wouldn't be having this lecture right here. But it's not that simple. Some drugs are going to remain mostly in the plasma. So if I put the drug in the plasma, it doesn't go to the rest of the body. It stays in the plasma. Then there's a very small volume of distribution. If I put the drug in plasma and it's all extensively distributed to the rest of the body and not much of it remains in plasma, I have a very large volume of distribution. So the volume of distribution tells us abstractly how extensively is distributed the rest of the body compared to the plasma. If the volume of distribution is very small, then the drug remains in the plasma. If the volume of distribution is very large, that means it's being pulled out of the plasma. And so there's a equation for that. The volume of distribution is equal to the amount of drug in body over the plasma concentration. And the volume of distribution, we can abbreviate it just like that. All right, so we're going to take 50 milligrams of drug A, and after we administer the drug, the plasma concentration of the drug is 0.1 milligrams per liter. That means the volume of distribution is 50 over 0.1. 50 over 0.1 is 500. All right. So again, if the 50 milligram dose resulted in 0.1 milligram of drug per liter of plasma, that means the volume of distribution for drug A is 500 liters. Now our total body water is 42 liters. How does a volume of distribution get up to 500 liters? And the largest volume of distributions that you'll see is somewhere 470s in that area. All right, so 500, that's a very large volume of distribution. And so how is it that we have a volume of distribution that's 500? Well, again, the volume of distribution is an abstract concept. It's not an actual volume. All right, and so in this case, we put the drug into the plasma and it was extensively distributed to the rest of the body, not leaving much concentration in the plasma at all. And so if we add the drug and it's extensively distributed to the rest of the body and we're left with a plasma concentration of 0.1 milligram, that's the equivalent of adding the drug to 500 liters of plasma. So that's, you're basically you're basically saying that if you put the 50 milligrams of drug into 500 liters of plasma, then you'll end up with a concentration of 0.1. And that's the point that we're trying to make here, that the volume of distribution is not an actual volume. The volume of distribution is actually what the size of the plasma compartment would need to be if that drug was only placed into one compartment. So hopefully that makes sense. If you see board questions that say, oh, well, no volume of distribution can be greater than the volume of the body water, and that's not the case at all. The volume of distribution can be very large, usually not larger than 500 liters. So it abstractly tells us in terms of the plasma as a single lone compartment. If I put 50 milligrams into the plasma and I end up with a concentration of 0.1, then that's the equivalent of the plasma compartment abstractly being 500 liters. And so it's not an actual volume at all. However, this is why we use it, and this is why it's so important. It's easy to measure. We know the drug, we know the dose that we've given, and we can measure the concentration with a blood test. And then once we know the volume of distribution, those two things, there's all sorts of calculations that are essential in pharmacology that will come from the volume of distribution. So take some time to think about the volume of distribution and understand conceptually what that means. You'll have a better understanding of some of the interesting things that we see in pharmacology. You give a drug and then it's not in solution. Why? Because of extensive binding in other parts of the body. So that gets us to loading dose, an initial dose of a drug that's given to get the drug up to target concentration. And so maybe you guys know about a Zithromax Z-Pak. You take 2 today and then you take 1 a day after that. Well, the 2 you take on the first day, that's a loading dose. When we're giving IV medications, it gets more complicated than that. We can give a large dose to get somebody up to a target concentration and then give them a dose after that, like heparin. When we start the math sections, there's a heparin loading dose. We give them a big dose of heparin to get them to a certain target concentration, and then we'll give them a heparin drip after that to maintain a maintenance dose. So a loading dose is used for all sorts of reasons, especially drugs that are eliminated from the body very slowly. We'll load those up. And so the loading dose is going to just be equal to the target concentration that we're looking for times the volume of distribution. And so that's what's fun about the volume of distribution, is that once we know that, it's very simple to come up with a loading dose, because it's equal to the target concentration that we want times the volume of distribution of that drug. So after the loading dose, the dose levels are maintained by a smaller maintenance dose, a drip, and that brings us to the clearance times the target concentration. And clearance is a first-order process where elimination is determined by concentration. All right, let's talk about protein binding. This is a source of a lot of confusion in the clinical setting, and so I want you guys to take time to think about this. I get emails about once a year from somebody who sees this, and I was talking to a pharmacologist the other day who is aware of this, and so let's talk about protein binding. There are many types of proteins in the blood plasma, and we'll just call them binding proteins. Albumin is certainly one of them. And these proteins will bind all sorts of drugs, and they'll be called protein binding drugs, highly protein bound drugs. Right? Now these proteins, they act like sponges, and they sponge up the drug. Once the drug sticks to the proteins, nothing happens. They're not the actual receptors that cause something to happen. These big proteins that float around in our blood, they'll just suck up drug like a big sponge. And then when those drugs are attached to those proteins that float around the blood, well, they're not able to activate receptors until they're free. That's an important concept right here. And when they're protein bound, they're not able to activate receptors. And so these proteins, like albumin, they'll act like a sponge on these drugs, and the drugs will need a loading dose to fill those protein binding sites so we can have free drug from the binding sites. All right, so here's the cartoon that we're going to use. These are my drug binding proteins like albumin. And then these are the receptors that the drug needs to work upon. And so when the drug is interacting with these receptors, then we get an effect of the drug. But when the drug is stuck to these binding proteins, then they're not free in solution to activate the receptor. All right, so we're going to add 6 units of any drug A, and it's protein bound. And notice that after adding 6 units of drug A, we have 0 effect because the drug can't interact with its receptor due to protein binding. All right, well, let's just, instead of adding 6, we're going to add 8. All right, well, we've added 8 units of drug here. There's 8 units of drug. It's all protein bound. There's no drug to activate receptors. Even if we add the 10 units of drug, we're still protein bound at this point. We don't have any free drug. So in this cartoon, it takes 12 units of drug A, quite simply, to saturate the protein binding sites. It'll be in doses above 12 units of drug A that we finally have free drug to activate receptor. And so now here at 13 units of drug A, I finally have free drug in solution that can activate receptors. All right, so if I add more drug, I've saturated the binding sites already, and then I can activate more receptors. So here's the punchline right here. Starting or stopping a drug that binds to plasma protein will change levels of other protein-bound drugs. And this is very confusing for people, how changing one drug is going to change the drug levels of another drug. All right, well, here are my drug binding proteins, and notice that we've loaded them up with 12 units of drug A, and so the protein binding sites are completely saturated with drug A. All right, well, let's add drug B. All right. And notice when I add 6 units of drug B, well, I don't have any drug B in solution. I don't get any effect from drug B whatsoever. I add 6 units of drug B, and what do I get? I get an increase in the level of drug A in the solution. All right, so now I've made drug A plasma levels go up quite simply by adding drug B, and drug B displaced drug A from the protein binding sites, raising levels of drug A. And so when we use multiple drugs that compete for these drug binding sites, sometimes we can get more of an effect from one drug quite simply by adding a different drug. All right, so this happens commonly enough for me to get an email about it about once a year. And let's cause a seizure by stopping a blood thinner. All right, so this person's going to the hospital for some kind of surgery, and they're taking warfarin, which is Coumadin. It's a blood thinner. Maybe they have atrial fibrillation, and they're doing things old school and using warfarin, Coumadin, as a blood thinner. Well, they also have a seizure disorder, and they're taking phenytoin, which is a dilantin, an anticonvulsant, an anti-seizure drug. And so both of these levels have been checked, and both of these levels are looking great. And they come into the hospital for a surgery. And by the way, both Coumadin and dilantin are some of the most highly plasma protein binding drugs out there. That's why the interaction between the two is really incredible. All right, well, it's 3 days before surgery, and naturally the surgeon wants the Coumadin, the blood thinner, to be stopped. That makes sense. We don't want them to bleed excessively in surgery. And there's some things that we can do to decrease the effect of the Coumadin over time, and we'll talk about that when we talk about blood thinners. All right, so 3 days before the surgery, the blood thinner stopped. That makes sense. We don't want them to bleed during surgery. And the Coumadin was stopped, and it was protein bound, but because it was stopped, this left protein binding sites available for dilantin. And those extra binding sites absorb the dilantin out of solution, out of the plasma, causing less dilantin to be available to the receptors to prevent seizure. And so let's see it again. All right, so here we're saturated with drug A and drug B. And I think drug A is our Coumadin and drug B is our dilantin. And so my protein binding sites are nice and saturated, and I have adequate levels of drug A to interact and affect drug A receptors. I have plenty of drug B in solution to interact with drug B receptors and get that effect. So I'm getting the Coumadin effect, I'm getting the dilantin effect. All right, so we're going to discontinue drug A. We're going to discontinue this Coumadin for surgery. Right? And so by discontinuing the Coumadin for surgery, what have we done? We've taken drug A out of the picture, and what has happened now? The drug binding sites are available, and so there's no drug A. That means the drug binding sites are not saturated, and what they're going to do is pull drug B out of solution, so the drug B cannot activate its receptors. And so this is how we can cause seizures quite simply, by stopping a blood thinner if the person is taking both a blood thinner and an anticonvulsant. So this is very important with toxic interactions. Starting or stopping one drug that binds to plasma protein is going to change the level of other protein-bound drugs. I get questions about this all the time. If I prescribe something, the pharmacist will come back and say, well, these things are protein bound. They're both protein bound drugs. And if we're using the medication in a short term, then this isn't so much of a problem. But if we're using medications in the long term, then this becomes very, very important to be aware of right here. So I want you guys to spend some extra time going back and thinking about this, because if you pay attention, you're going to find that there's all sorts of interesting, not so good things that occur in the clinical setting because of a lack of understanding of this concept right here. Oh, goody. Well, that is more than enough for this lecture. When we come back, we're going to talk about 1.5, even more basic principles in pharmacology. So until then, aloha.